Okay, welcome all. I'm going to explain in this video about data interpretation. So, if you have data from experiment, how you can interpret it, how you can plot it, and so on. Okay, so this will be about conversion versus residence time. Okay, uh, suppose we have PFR, plug flow reactor or tubular reactor. Okay, volume is given and initial concentration is given, rate constant is given. This is first order reaction. Okay, and then you have measured the concentration against different flow rate. So suppose you did the experiment. Now you can see the excel. So if you did the experiment and you measure the exit concentration, exit coming out from the reactor. So these are CA out at different feed flow rate. Okay, these are the raw data. Okay, and we want to study how the conversion is changing with feed flow rate or basically residence time. So feed flow rate is depending affects residence time, right? So first of all, what we can do, we can find the conversion XA. Okay, XA here, XA, which will be CA naught. CA naught is given, so it's 2 mole per liter. CA naught minus CA out divided by CA naught, right? So this is the conversion, and this now we have conversion versus feed flow rate. So our job is to plot conversion versus residence time. Okay, residence time. So residence time tau, if you remember, is volume of the reactor, which is 100 liter, 100 divided by the feed flow rate. Feed flow rate. This will be in minute. So residence time is 20, conversion is 97.5. Okay, so this is the residence time. We can make it 1 decimal point. Okay, so conversion versus residence time. So we can now plot. Always we will plot as a scattered data point. Experimental graph must be plotted as scattered, and then we will look for the base trend. What is the how to express this? So now we can see on y-axis we have conversion. On y-axis we have conversion, and on x-axis we have residence time. Okay, so conversion is increasing with increase in residence time, which makes sense because as reactant feed will stay more in reactor, it will convert more, right? So that's the residence time. So now how to fit this is a train. What is a train? So you can see that it's not linear, right? Whenever you have experimental data, there is temptation to fit a trend line, and sometimes or most of the times trend go for the linear. Even linear, if you fit it, and then you can see, okay, r square is 0.8 around, and one can say that it's okay, it's fitting, not bad. But theoretically, does it make sense? If it is linear, then conversion should increase always with increase in residence time. But conversion, now see, it's showing more than one, which is doesn't make sense. So it means that conversion will increase, and after some time it becomes, it may increase only a bit, or after, or it will be, it cannot be more than one. So trend is something like this. Now, how to relate this theoretically? Do we have a relation, a mathematical expression which relates conversion and residence time? Yes, most likely we will have. So what we can do, we can uh, do some mathematics. So if you remember, design equation of PFR, this is the design equation of PFR, right? RA, this is we said that this is first order reaction. So RA will be KCA, right? KCA, and then CA is CA naught 1 minus XA, right? DXA K CA naught 1 minus XA, and we have here K over C, tau over, sorry, tau over CA naught. CA naught will get cancelled. This one K tau equal integral of 0 to XA, right? So this will be ln 1 minus XA with minus, and from 0 to XA. Okay, so if you apply the limits, uh, first thing will be minus ln over XA, and then minus XA 0 ln 1. Ln 1 is 0. So we have this K tau equals, so if you, we want conversion versus residence time. So 1 minus XA equal minus K tau, sorry, ln. So 1 minus XA will be e power minus K tau, right? And then XA is 1 minus, so this is the relation we were looking for. So as you can see, residence time goes to infinity, conversion will be 1 maximum, and when residence time is 0, conversion is e power 0 is 1, 1 minus 1, 1 is 0. So this makes sense. So this is the expression we have. Now so what we can do, we can get the for theoretical. This is the theoretical equation, right? So using the theoretical values, we can find XA theoretical, which is 1 minus exponential minus K tau. The value of K is 0.2 times tau is residence time, right? That's the theoretical value. Okay. Now we can add here the theoretical conversion. Sorry, add theoretical conversion versus residence time. You can see that they are close to each other, but there is deviation because we had experimental results. So this is an equation, so we should fit not scattered, smooth graph. Okay, so that's the red line is theoretical. So we can have legend. Okay, okay, edit. You can say experimental series 2 theoretical. Okay, so visually you can see that they are close to each other, and then we can add some statistical analysis to show that how is the deviation. So error between theoretical and experimental minus theoretical, sorry, theoretical minus experimental divided by theoretical. So we are comparing with theoretical. This is, sometimes we have positive, sometimes we have negative. So what you can do, say that the maximum you can include the worst scenario, and you can say that my maximum error is 29%. Okay, so one scenario doesn't mean that it is really bad. This is experimental data. So we can represent in better way to add, when we add average error. So for the averaging you need to calculate the absolute. So you find the absolute error, then it's called AAD, average absolute deviation. So it will be average of all these. Okay, so this is AAD. So you can include like, okay, your worst scenario, then you can say the average. So average is 12%, which means that most of the data points are okay, are good. And then what you can do, you can, for example, here we can check the rate constant values. How close are they? Rate constant value of the reaction. So let me calculate with the same equation. We had the equation, this one, right? This one. So from here we can get the K. So K means K is minus ln1 minus xa, this is experimental, divided by tau, residence time. So this is the x, rate constant K, experimental, theoretical is 0.2. So now we see it is moving around, increase decrease around 0.2. We change the feed flow rate. Feed flow rate should not affect the conversion, should not affect the rate constant, because rate constant of a reaction is as a property of the reaction. It depends only on temperature. K depends on temperature. So whatever you see, the deviation here, it is mainly just scattering. This is just deviation because of experiment. So what we can do, we can find the average K. So it will show, represent better. So you have the average K, and you know that the theoretical value is 0.2. So it's quite close, right? And then to justify further, you can find the standard deviation. Okay, it means how much it is deviating. STED, you can standard deviation, normal one, this one, choose. So In that case, we can say that deviation is around 0.38 or 0.04. Okay, so your experimental value 0.19, then you can say 0.19 plus minus 0.04. So deviation is not much. So k value is almost constant with respect to the residence time or feed flow rate is not affecting. So it is proving what we learned in reaction engineering course. To do it further, what you can do, you can plot this. You can plot this versus against flow rate. See, if you put this, see, it's showing sinusoidal. So it may misguide you. So just use this one and then add the x-axis, and the x-axis is time, residence time. Okay, so these values, some of them showing this one, so it's showing deviation, but because the scale is also very close. So what we can do, we can increase the minimum and maximum. Okay, so this scale we can also increase. 0. Oh, okay, it is the minimum around value is 0. Okay, so 0 and then maybe 0.5. So you can see that they are almost close to each other. So what we can do, we can plot the average. Put all average here, one value. So it will be a horizontal line, and so this almost close to. So this is the horizontal line, and there is a deviation at a small residence time. Basically, we have more experimental error, and then this is almost close to this horizontal line. So there is deviation, experimental deviation going on. So k is almost constant with respect to the residence time, which makes sense because k depends only on temperature. Okay, so these are just like any data you have, you can approach like this. So plot it, get the trend, try to make sense of the trend. Okay, try to justify the reason. Then theoretically, what should be the trend? Look for any mathematical equation you have, relate it, find the error, find the AAD, find the standard deviation, and then you can use all these statistical terms in your report discussion. Okay, hope it was helpful. Thank you.